7.7 System of Inequalities and Linear Programming. So let's talk about how to solve a system of linear inequalities. And it's just a linear system with an inequality instead of an equal sign. And then when we solve this is by shading. So let's talk about how to do that. First, when we shade, in general, if you have greater than, you want to be above the line, because you're greater than. If you have less than, you want to be below the line. Because remember, our equation is the line. So if you're saying you're greater than the line. If you're saying less than, below the line. Don't forget also how to make the line. If it's just greater than or less than, then it's a dashed line. If it's greater than, equal to, or less than, equal to, it's a solid line. That's kind of done like the normal, like you kind of graph it normally. So let's graph the linear equation. So we have this. Generally, we want to graph. We want to put it in slope intercept form. Y equals mx plus b. So let's move over to this x. I'm going to get 4y is greater than negative x plus 4. We're going to divide everything by 4. So y is greater than negative 1/4 x plus 1. So this is what we're going to graph. So let's make a little thing here. Remember the way we graph, you start with the y-intercept. My y-intercept here is 1, so we're going to start at 1. Then we go to the slope. The slope here is negative 1/4, so that means we're going to go down 1 and over 4. Right, rise over run. So we're going to go down 1 over 4, right there. Now again, notice that this is not, there's no equal to sign, so it's going to be a dashed line. Through those 2 points. There's our line. And now, so this is our y, this is our equation, y equals, and I'm saying greater than that. We want greater than that. So I'm going to shade all above it. And there we go. That's our solution set right here. Now there's generally 2 ways to graph, to shade. One way I showed right now is to shade by understanding that less than greater than. This is only works when it's in proper notation, which is y equals mx plus b like this. If it's flipped around, it's going to be a little funkier. Another way to do it is by doing test points. So if you're not sure, you could do a test point. So what does that mean? You pick any point on the graph, so let's say 0, 0, and you plug it into your equation. So my equation is this right here. So we're going to plug it into this guy. So I'm plug 0 is greater than negative 1/4 times 0 plus 1, and I get 0 is greater than 1. If you notice, that is not a true statement. 0 is not bigger than 1. That's why it's not shaded here. So if you get a false statement, you shade the opposite side. If you get a true statement, you shade that side. So in this case, we got false. We shaded the opposite. That's the idea. Okay, let's graph another one. So we're going to graph this guy. Now again, notice, if you notice where this formula is, it's the exact same thing as y is equal to 1 over x minus 1, but with an inequality, we shade greater than instead. This is a reciprocal function. So let's find the horizontal asymptote and the vertical asymptote. If you remember, the horizontal asymptote is the powers. The bottom power is bigger than 0, bigger than the top, so it's 0. If you remember the way you find the vertical asymptote, you said the denominator equal to 0. So I'm going to get x minus 1 equal to 0, and I get x equals 1. So here's my equation. Something like this. Alright, so we have horizontal asymptote at y equals 0, so right here. We have vertical asymptote at x equals 1. And then remember, this is a positive, so my graph's going to be on the top right side. So my graph's going to look kind of like this. Now it is a solid line, because it's equal to, so it's going to look kind of like this. And it's also going to be here. So like that. Then I need a shade. Again, we are greater than, so we want to be above our line. So here's our line, we want to be above it. So it's going to be all the stuff in here. We want to be greater than, or in this case, greater than this guy, so it's going to be all the stuff right here. Alright, all that stuff would be greater than the line. And that should include the top too. Almost forgot the top. So all of this is all greater than the graph. Now, one thing I can do, I cannot go past this vertical asymptote here, but everything above the graph from here to here is part of the answer. So that's the idea. So if you have an inequality, only difference is now you graph it. And greater than means graph shade above, less than shade below. If you're not sure, you can always plug in a test point. Like in this case, if I were to plug in the test point of, let's say, 0, 3. So you just plug it into this equation here, and we get 3 is greater than 1 over 0 minus 1, which is saying 3 is greater than negative 1. That is a true statement. 3 is greater than negative 1. So I would shade where that test point is. So I would shade over here, which I already did. So again, either greater than means above, less than means below, or do the test point. How do you graph a system with two inequalities? Well, basically you graph each one separately and then see where they shade. See where they cross shade at. So let's do them real quick. Make one little graph here first. Here's my X and here's my Y. Let's do top one in blue. So this is another linear system. So again, when you want to graph a linear system, you want to put y equals mx plus b. So let's move over to 2y. So 2y plus x is greater than 6. Subtract the x from both sides. 2y is greater than negative x plus 6. Divide by everything by 2. Y is greater than negative 1/2 x plus 3. So start at 3. Slope of negative 1/2, so I'm going to go down 1 and over 2. So something like that. It is not greater than equal to. It's just greater than, so dash line. There's no equal to sign there. And then I'm going to shade above greater than. So let me try to make this a little nicer. I'm going to shade with actual shading. So something to that effect. Okay, so that's the first one. Now let's graph the second one. So I'll tell you right now, usually you want the y on the left-hand side. So I'm going to actually flip this around real quick. I'm going to make that 2y is greater than x squared. So I'll make it like that. Then I'm just going to divide by 2. So y is greater than 1/2 x squared. So if you remember how to graph a parabola, our vertex is 0, 0. Because there's no horizontal and there's no vertical flip. And my slope is 1/2. Well, kind of like the slope. So it's 0, 0, and I'm going to go over 2 and up 1. Over, I shouldn't say that. You go over, we're going to go over 1 and up 1/2. So kind of like that. Now what's going to happen here is, it's a parabola, so let me do a dashed line again. Kind of like this. And then where do I shade? I shade greater than, so above again. So let's change this to purple. I'm going to shade inside. So I get that. So where's my answer is where they both shade. So where both these graphs shade, which would be right here. Let's say right there. So this little section right there is my answer. That's how I solve a system of inequalities. You just graph both of them and see where they both shade. There we go. Let's talk about linear programming next. Linear programming is a important part of business mathematics. We use it to optimize value or to minimize costs. So it's a hugely important branch of mathematics in general. So that's what we're going to look at here. So I'm going to give you this linear program. So eventually we're going to have to make this part ourselves. But in this case, like here is our little region that we linear program. I want to find the max value, the max and min value of this function here. So we call this the optimizing function. So we're trying to optimize this. So a lot of times we'll say z equals 6x plus y. We're trying to optimize it. So how do we optimize it? Really simple. We just plug in all our endpoints here into our optimizing function. Highest value is the max, lowest value is the min. That's it. So we're just going to sub in and find max and min. Right, so once you get down to this point, it's actually a really easy problem. You just go, okay, I have my linear program little area right here. All I gotta do is plug all my endpoints into this value right there. So let's do z of 1.15. So I'm gonna get 6 times 1 plus 5. Right, when you have a point here, that's your x and that's your y. So you plug in for x and y. You get 11. Z of 6/8. So 6 times 6 plus 8. So 36 plus 8 is 44. Z of 9/1. 6 times 9 plus 1. So 54 plus 1 is 55. And then z of 1/2. So 6 times 1 plus 2. And I get 8. So my max is right here. At the point 9, 1, I get a max of 55. And my min is right here. At the 0.12, I get a minimum of 8. And we just optimize that. Okay, so now how do we work our way backwards? How do we get to this point where we have our little range right there? Well, to do that, we got to follow a couple steps. So first, the fundamental difference in linear programming, this says, hey, if you want to find the max and minimum region, like the optimal value, it has to happen out. It happens at one of the vertex points. So like right here, the max is not going to happen in between here. It's going to happen on one of these vertex points. So that's where the max happens. So how do we find those max values? Well, the whole problem is this. We're going to write the objective function and all the necessary constraints. So we'll write down everything they tell us. What's our objective function? What are all the constraints? We'll graph the region with all feasible solutions. We'll identify all the vertex corner points. Then we'll type those values into our objective function to find the max. And then we'll state what our max is in the vertex form. So let's do a couple examples. Example here first. A company makes 2 products, MP3 players and Blu-ray players. This is an old problem. Each MP3 player gives a profit of $30, while each Blu-ray player produces a profit of $7. The company must manufacture at least 10 MP3 players to satisfy one of its customers, but no more than 50 because of the production restrictions. The number of Blu-ray players cannot exceed 60 per day, and the number of MP3 players cannot exceed the number of Blu-ray players. How many of each should the company manufacture to attain max profit? So a lot of stuff they're throwing out for us. First, we want to try to find the optimizing function z. So, and that's what we're trying to optimize, which is our profit. So MP3 players will say that's X, and Blu-ray players will say that's Y. I get a profit of $30 per MP3 player, so 30X. And then we get $70 per Blu-ray player, 70Y. So that's our optimizing function. Now let's get our constraints. So the company must make at least 10 MP3 players. So they're saying X has to be greater than or equal to 10. So let's have what at least means. So X must be greater than or equal to 10 to satisfy one of its customers, but cannot exceed more than 50. So I can't make it made for it. So that means X must be less than or equal to 50. Because I have to make more than 10, but I can't make more than 50. The number of Blu-ray players is Y cannot exceed 60 per day. So I can't go past 60 per day. So Y is greater than or equal to 60. Sorry, less than or equal to 60. The number of Blu-ray players cannot exceed 60 per day, and the number of MP3 players cannot exceed the number of Blu-ray players. So the number of MP3 players, that's X, cannot be bigger than the number of Blu-ray players. So X must be less than or equal to Y. These are all our constraints. So let's have X must be bigger than 10, but less than 50. Y must be less than 60, and then X must be less than or equal to Y. So what we're going to do is we're going to graph all these constraints. So usually when we do a linear programming problem, we only do the positive X and Y axis. Something like this. And let's count by what, tens, maybe? 10, 20, 30, 40, 50, 60. 10, 20, 30, 40, 50, 60, 70. So something like that. Here's my X, which is again MP3 players, and here's my Y, Blu-ray players. So all we have to do is plot these. So X has to be greater than or equal to 10. Well, remember the way you plot that is here's X and go to 10 and draw a straight line. Like that. Now X must be greater than that, so I'm going to shade this section of it. Just for the sake of it, I'm going to leave it blank for now. X must be less than 50. So, same idea, go to 50 on your X. And again, I'm going to be less than that, so I'm actually shading this middle portion right here. This is where I'm kind of shading right now. I need Y to be less than 60. So, here's my Y, go to 60, which would be right here. Draw a line. And again, I want to be less than that, so I'm going to go below this. So like right now, I'm shading this way, and this way. Now I got to graph one more thing. X is less than Y. Now it's a little funky for us. We usually don't graph X less than Y, but let's rearrange it. Y is greater than or equal to X. It's the exact same thing. This we know how to graph. Remember the trick to graphing this, you make this a plus 0. So this is saying I have a y-intercept of 0, and a slope of 1. So you start at 0, 0, and you go up 1 over 1, or up 10 over 10. And I get a line that looks like this. And I want to shade above this. So my shading should be all right here, right in the middle of this guy. So like that. So that's what I'm trying to optimize. Now remember, to optimize, all I gotta do is plug in all these endpoints right here, corner points we call it, into this optimizing function. Highest value is our maximum function. So how do we find that corner point? It's actually, some of it's not that bad. This point right here, well, what's my x? 10. What's my y? 60. So point 10 and 60. Over here, x is 50, y is 60. So 50, 60. And now we get to the slanted one. It's a little worse. Now, I know what the x value is. X value is 50. Because it's on this line. How do you find the y value? Well, you can plug it into the equation, right? There's an equation for this line. The equation of this line is y equals x. So, if x equals 50, that means it's plugged into the equation, y equals 50. The same thing goes true for down here. I know what the x value is. It's 10. How do you find the y value? Plug it into the equation. If x equals 10, y equals 10. So those are the points I need to test. I need to test 10, 6, 10, 10, 50, 50, 50, 60. Whichever one of those gives me the highest value here is my maximum function. It gives me max profit. So let's plug them in. Z of 10, 60, 30 times 10, plus 70 times 60. So 4,200 plus 300, so 720. Feel free to use a calculator. Z of 50, 60 equals 30 times 50 plus 70 times 60. So 4,200 plus 1,500. Alright, so this is 4,200. And this is, well, 300. 42. Forgot a 0 on that one. Sorry about that. I actually added wrong on that one in general. No? Okay, so yeah, 4500. Just making sure I did that right. And then this one would be 1,500. So I'm going to get 570. Like that. And then we do, let's go around Z 50, 50. So 30, 50 plus 70, 50. 3,500, 1,500. So what's that? 5,000. And then Z 10, 10. Probably not going to be the max. 30, 10 plus 70, 10. So 700 plus 300 equals 1,000. So out of those, again, I'm trying to maximize profit. That would be right here. Max profit to right there. So my maximum profit, it's from the point 50, 60, which means I make 50 MP3 players and 60 Blu-ray players. And that's the problem. We're going to do one more to make sure we have this, but that's the general idea. We do an optimization function. We write down our constraints. We graph our constraints, because it's a little section right here. And then once we find the endpoints, corner points, we plug them into our optimizing function to find the max or the min. Okay, let's do one more. Shipping costs. A manufacturer of refrigerators must ship at least 100 refrigerators to its West Coast warehouses. Each warehouse holds a maximum of 100 refrigerators. Warehouse A holds 25 refrigerators already, while Warehouse B has 20 on hand. It costs $12 to ship to refrigerator warehouse A and $10 to ship to warehouse B. How many refrigerators should be shipped to each warehouse to minimize costs? We're actually trying to find the minimal cost with the lowest value this time. Okay, let's try to find our optimizing function. That is going to be the cost. We're trying to minimize cost. So what's the cost? Warehouse A is $10 per thing we ship, and warehouse B is warehouse A is $12 and warehouse B is $10. So we're going to say, let's call warehouse A X. So it's going to be 12X plus 10Y. Right, so warehouse A would be X, warehouse B would be B. So that's our optimizing function. Now how about our constraints? So the manufacturer must ship at least 100 refrigerators to 2 warehouses. So if I add X plus Y, it must be greater greater than or equal to 100. Right, I have to ship at least 100 refrigerators to both of those warehouses together. So if I add 2 warehouses, it has to be greater than 100. Each warehouse holds a maximum of 100 refrigerators, so they're saying X must be less than 100, and Y must be less than 100. Warehouse A holds 25 refrigerators already, warehouse B has 20 on hand. So actually it probably should be X is 100, but let's subtract off 25, and then Y is 100 minus 20. So really these should just be X is less than or equal to 85, and Y is less than or equal to 80. Because they already have that many in hand. So those are my constraints. We have this guy, we have these two. So those are my 3 constraints, and I have this optimizing function. Okay, let's try to graph this. When we graph these, we really want to graph the positive X and Y axis. That. Let's go by 10 again. Let me go by 12. It doesn't matter. Let's go by 10s again. So it'll be 10, 20, 30, 40, 50, 60, 70, 80, 90. Same thing up here. 10, 20, 30, 40, 50, 60, 80, 90. So sudden side effect. Okay, now we gotta graph all the constraints. Let me move this one down here also. X plus Y equal to 100. So again, some of these constraints are easy to graph. X less than 85, easy. Where's X? Where's 85? Right here. I want to be less than that. Y has to be less than 80. So here's 80 on my Y. So to be less than that. Then this one right here, X plus Y must be greater than or equal to 100. So again, how do you graph that? Well, we got to get Y by itself. So Y must be greater than or equal to 100 minus X. So that's this one. How do you graph that? Rearrange it a little bit. So you gotta go up to 100, which I don't have yet. And we gotta go down 1 over 1, or down 10 over 10. So that's this one right here. So I go up to 100. My slope is -1, so I'm gonna go down 1 over 1, or down 10 over 10. And I'm gonna get something that looks like this. All the way down. Since that effect. And then this is where we're trying to optimize, this little region here. Now remember the general idea here is we want to minimize costs. So we're trying to find the minimum cost here. So what I do next, I gotta find all these endpoints. One of them is super easy, right there. X is 85, Y is 80. Done. Now remember, to find the one on the slanted line, we know some information on these two. On this one, I know the Y is 80. The one right here, we know that X is 85. How do I figure out what the X is here and what the Y is there? Well, don't forget there's an equation that connects to this. And that equation is X plus Y equals 100. Right? That's the equation for this line. So, if I know Y is 80, I could plug it in, I figure out X, subtract 80 from both sides, and I get X is 20. Right? 20 plus 80 equals 100. Over here, I know X is 85, plug in 85, solve for Y, you get 15. So those are all my corner points. All I have to do now is plug all 3 of them into this equation, figure out what the minimum is. So let's find the min. So again, my function is 12x plus 10y. And what I'll do is plug in every single of these endpoints. So let's start with the first one, the z of 2080. So I get 12 times 20 plus 10 times 80. Again, feel free to use a calculator. I get 800 plus 240. So I get 1040. Z of 8580. My guess is this is not going to be the min. So 12 times 85 plus 10 times 80. So I get 800 plus 850 plus another one. Was that? Let's see. It's 850. This is going to be like almost like 9 something. 930, 640-ish. It's gonna be like 1700. It's gonna be way too big. So not that one. And then we have Z of 85 and 15, which is 12 times 85 plus 10 times 15. So this is 150, and this is 1020. So you add them up, and you get 170. So the minimum cost is right here. Min cost is 2080, which means send 20 to warehouse A and 80 to warehouse B. And that's the lesson.